Jai Hind everyone. This is Dr. Naresh Kumar from Akgec Engineering College, Ghaziabad. Welcome to the class of optical communication. In this new video lecture, we will discuss the topic optical fiber structure along with the concept of ray theory. So as discussed, the main contents for this lecture will be optical fiber as a waveguide, or what is the structure of optical fiber, what are the various layers present in the case of optical fiber, and why we are considering this as an waveguide or equivalent to waveguide. And next we will discuss the concept of ray theory, and the main topics covered in this will be total internal reflection, acceptance angle, and then we will discuss the numerical aperture. So first of all, we have studied that in the optical fiber communication system, the channel is replaced by a special guided media known as optical fiber cable. So in the optical communication, we are using the optical fiber cable as a channel, and we know that this optical fiber is generally made up of glass or plastic. Glass or plastic. Basically, the optical fiber has various layers with refractive index varying. In the optical fiber structure, we have basically two layers. The inner layer is known as the core and outer layer is known as the cladding. And in the optical fiber structure, to ensure the propagation of light through the fiber, we ensure that the refractive index of core, that is N1, should always be greater than the refractive index of the cladding, that is N2. So in the optical fiber structure, we mainly have the two layers, that is the inner layer core with refractive index N1, outer layer cladding with refractive index N2, and to ensure the propagation of light, so that the principle of propagation of light inside the fiber is followed, that is total internal reflection, to ensure the process of TIR, so that light may propagate from one end to another end. We ensure that the refractive index of the core is always greater than that of the cladding. Now the question arises, why we are saying the optical fiber as a optical fiber waveguide? This name has been given because of the similarity and comparison with the metallic waveguide. We basically know that there are metallic waveguides which are hollow metallic portions which are used for propagation of electromagnetic waves due to multiple reflections from the inner walls. As the electromagnetic wave propagates through these metallic waveguides, in the similar way, the light propagates through this optical fiber cable due to multiple reflections at the core cladding interface by following the principle of total internal reflection. Moreover, these metallic waveguide are also the wired media, and optical fiber is also a wired media. So because of this similarity in the structure as well as in the working principle or propagation of signal, these optical fiber cables are also termed as optical fiber waveguide. And moreover, we have the inner layer as core, outer layer as cladding. Now to give the mechanical strength to this fiber and overall to protect the fiber, at the outer of this cladding we may have some kind of mesh, some kind of plastic layer to give a mechanical strength as well as for the protection purpose. And moreover, this outer layer, preferably known as the jacket, this jacket can be compressible in nature also, so that it can bear the pressure or to maintain the uniform lateral pressure over the fiber when using the fiber into the practical conditions. This is the basic optical fiber structure that has been shown here. As discussed, there are three main layers. Inner layer is core with refractive index N2. Then we have outer layer with refractive index N2. Then to ensure the TIR, as discussed, we ensure refractive index of core is greater than the cladding. And moreover, for the protection purpose and to give the mechanical strength to the fiber, we may have a outer buffer coating, or also known as the plastic coating, also known as the jacket. So this is the main basic structure. Then the working principle of optical fiber or propagation of light in the fiber can be explained through the ray theory or ray geometric optics. So basically, propagation of light inside the fiber, light propagation, can be explained either using ray theory, also known as the geometric optics, and another is known as the wave theory. Okay, so first of all, we will have a brief discussion about these ray theory and wave theory. In the ray theory, light is considered as a ray. Light is considered as a ray of light, simply ray of light. And moreover, this ray theory is basically an approximate theory, and this can be applied when the dimensions of the optical fiber are sufficiently large. This can be applied when dimensions are sufficiently large. Whereas in the case of wave theory, light is considered as a wave similar to electromagnetic wave. As the electromagnetic wave has electric field component and magnetic field component, in the similar way, this light may also have a light field component, and this field component propagates through the optical fiber cable. So in the wave theory, light is considered as a wave having the field component which propagates through the optical fiber cable similar to the electromagnetic wave. And moreover, if we compare these two theories, this wave theory is generally or comparatively more accurate. This wave theory is more accurate, and this can be applied even when the dimensions of the optical fiber are not sufficiently large, or we can say that when the dimensions of the optical fiber are also not sufficiently large, in that case also we can apply the wave theory. So this is the basic difference or comparison of the two theories. So first of all, in this lecture we are going to cover the ray theory concept. We are applying the ray theory concept to explain the propagation of light inside the optical fiber cable. So to explain this ray theory or ray geometrics, we will consider a few points. That light is considered as a simple ray. We will apply the rule of geometric optics, such as we will apply Snell's law. Okay, and we will explain the propagation of light using this ray theory when the dimensions of the optical fiber are sufficiently large. So in this lecture, now we are going to discuss the principle of total internal reflection, also known as the TIR. Total internal reflection is basically the working principle of optical fiber cable, where the light propagates inside the optical fiber cable due to total internal reflection at the core cladding interface, and light propagates due to multiple reflections at the core cladding interface inside the fiber cable. So here we are discussing the phenomena of total internal reflection or working principle of optical fiber cable. So as discussed in the structure, this TIR takes place inside the fiber, and inside the fiber we know that there are two layers. One is core, another is cladding. Core has a refractive index of N1 and cladding has a refractive index of N2, and we ensure that refractive index of core is greater than the cladding. So we can say that if refractive index of core is more, we can say that this is a denser medium, and cladding refractive index is low, so we can say that this is a rare medium. Okay, so to ensure this, we have shown here there is a medium with refractive index N1, there is a medium with refractive index N2, and as in the discussed in the structure, N1 is greater than N2. So we can say that this is a denser medium and this is a rare medium. So there is incident ray, light is considered as a ray. So whenever the light is incidented at the core cladding interface from denser to rare medium, this is the incidented ray. Whenever a ray is incidented from denser to rare medium, it slightly bends away from the normal. This is the normal path if the ray has been straight, but the ray slightly bends away from the normal. This is the normal. Okay, so whenever we move from denser to rare medium, the ray slightly bends away from the normal. So it will bend away from the normal. So this is the exit ray. Now if we increase this is the angle of incidence. If we increase this angle further, then this ray will bend more away from the normal. There will be a stage when this angle of incidence will be such that the exit ray will be there at the core cladding interface. So up to this point we were having the refraction. Now we have the exit ray at the interface point, and if we increase the incident angle more than this angle, then there will be further more away from the normal. So in this case the reflection starts. So this point is the critical case. Okay, so the incidence, angle of incidence, where this angle in the medium 2 becomes 90 degree and exit ray is at this point at the core cladding interface. This is the critical condition and this angle becomes the critical angle. Denoted by phi c. That is, if angle of incidence equal to critical angle, this phi 1 equal to phi c, then we have this phi 2 equal to 90 degree. This is the critical condition or critical case. Okay, if angle of incidence is less than this critical angle, there will be refraction. If angle of incidence is greater than the critical angle, that is phi 1 is greater than phi c, then instead of refraction, the incidented ray is reflected back into the same medium. That is, both incident ray and exit ray lie in the same medium. So instead of refraction, the ray is totally internally reflected back into the same medium, or hence the phenomena of total internal reflection occurs, which is the basic working principle for the propagation of light inside the optical fiber cable. So this is shown here. This is the incident ray and this angle of incidence is phi is greater than phi c, then the exit ray is returned back into the same medium. So there is totally internal reflection. In the previous slide, we can apply the Snell's law. Snell's law says that the refractive index into one medium into sine of angle in that medium will be equal to refractive index in the second medium into sine of angle into that medium. So this is Snell's law. From this we can have this one, and we can apply the condition of critical angle here. At critical angle, we know that phi 1 becomes phi c and phi 2 becomes 90 degree. Okay, so here we can apply sine of phi c divided by sine 90 equal to n2 by n1. We know that sine 90 equal to 1, so sine of phi c equal to n2 by n1. From here we can calculate the critical angle as phi c equal to sine inverse n2 by n1. So in this way we can calculate the value of critical angle which is required for the propagation of light inside the optical fiber cable using the working principle of total internal reflection. That we have calculated in the previous slide. The value of critical angle we can calculate using the Snell's law. This is the diagram showing the propagation of light inside the optical fiber cable, and we know that the principle used will be total internal reflection. Light inside the fiber propagates due to multiple reflections from the core cladding interface. So when this light is moving, this is core, this is cladding. So at the core cladding interface, it is reflected back into the same medium. Again at this point, reflection will be there, and at this point again reflection will be there. So due to multiple reflections at the core cladding interface, light is propagating inside the optical fiber cable. Another term that is popularly used is acceptance angle. Basically, light inside the fiber is coming from a source. Source is optical source, for example LED or laser. LED or laser. Now, how we can place an optical source outside the fiber so that light entering into the fiber follows the condition of TIR and light can propagate through the fiber. This is assured through the acceptance angle. So acceptance angle is nothing but it is the angle which the light from the optical source is making with the axis of the fiber. It is the maximum allowed angle which the light entering into the fiber makes with the axis of the fiber, so that inside the fiber TIR can be followed and light can be propagated. That is, optical source can be placed within this range. That may be above this axis or below this axis, and this is known as the acceptance cone. This is the angle range within which if we place the optical source, then the light entering into the fiber will be such that inside the fiber condition of TIR will be followed, and if condition of TIR is fulfilled, then light will propagate. That is, if we place this light or optical source, angle is more than this theta A. This angle is more than this theta A, that is outside this point, these points. Then inside the fiber, the condition of TIR is not fulfilled and light will penetrate into the cladding. And light penetrated into the cladding does not propagate, it is eventually lost in the form of heat or radiation. So this is the condition required in terms of angle, and this is the maximum allowed angle which the light entering into the fiber makes with the axis of the fiber, so that TIR can be fulfilled. And we can calculate this as sine of theta A equal to numerical aperture. So theta A acceptance angle can be calculated as inverse of numerical aperture. That we have discussed. This is the modified form of acceptance angle. In terms of we can calculate this solid angle, solid acceptance angle, and we know that if for small values of theta A can be written as sine theta A, and we know that sine theta A will be equal to numerical aperture. So this solid acceptance angle can also be represented as pi of numerical aperture square. Then one more popular term is used with the ray theory is numerical aperture. Numerical aperture is basically the light gathering or collection capability of the fiber. Numerical aperture signifies a light gathering capability of the fiber. Light gathering or collection capability. That can be represented using a parameter known as the numerical aperture. Numerical aperture is basically simply a value, and it is a unitless quantity. And numerical aperture can be simply depend upon the refractive index of the core and cladding. So we can calculate the numerical aperture here. Basically this signifies the light gathering or collection capability of the fiber. So generally while calculating the power coupled inside the fiber or calculating the coupling efficiency, that is represented in terms of this numerical aperture. So we can derive this equation by applying this Snell's law at this point and at this point, that is n naught Snell's law, n naught sine of theta 1 equal to n1 inside this at this point sine of theta 2. This air is there, so n not equal to 1. At critical condition phi 1 becomes theta a, acceptance angle. So this becomes, left hand side becomes sine of theta a, and on the right hand side we have sine of theta 2. This theta 2 can be, using this right angle triangle, this theta 2 can be represented as 90 degree minus phi. At critical case, as we have taken this theta 1 equal to theta a, so this phi also becomes equal to phi c. So putting these value and doing the derivations, we can have this one. This is the Snell's law. Applying the value of theta 2 in terms of phi, so you have cos phi 1 minus sin phi. This critical case, putting the value as critical case, so we have sine of theta a equal to this one, and this is nothing but termed as the numerical aperture. So numerical aperture, which is the light gathering or collection capability of the fiber, can be simply represented in terms of refractive index of core and cladding. Significance of numerical aperture we have already discussed. It is the ability of the optical fiber system to collect light, that is light gathering or collection capability of the fiber, or power coupled inside the fiber, or coupling efficiency, that can be depending on the numerical aperture. So generally we have coupling efficiency equal to numerical aperture square, nearly equal to, whereas power coupled can be power in the medium, and then we have the brightness of the source, then we have the numerical aperture. So basically this numerical aperture signifies the light gathering or collection capability of the optical fiber. So that we have already discussed the significance. This is one numerical where we have the refractive index of core n1 is given, n2 is given. Then we can calculate the critical angle sine inverse n2 by n1, 78.5 degree. Then in the similar way we can calculate the numerical aperture if we are given n1 and n2. This is simply a unitless quantity, light gathering capability. Then we can also calculate the acceptance angle by using the relation with the numerical aperture, theta equal to sine inverse numerical aperture. Numerical aperture already calculated. So putting this, we can have the acceptance angle as 17.4. So if we are given with the n1 and n2 refractive index of core and cladding, which are generally made up of glass or plastic, having slight difference in the refractive index between the two, then other parameters can be easily calculated. So that's all for this lecture. Thank you everyone. This is the reference book that I have used. Jai Hind.